Are you ready? Okay. So, in this lecture, let's start looking again at the hills and valleys that we started with in the first lecture. Okay. So, in this graph, f of x represents height of the height. Okay, height as a function of x. Okay, so I have, let's say I want to know, so I have drawn this graph in a special way. It has some form here, okay, some functional form here, some functional form here, but in this region I have made it exactly, okay, assume it is exactly x square. Okay, I assume that it is x square. So in this range from, let's say, minus a to some b, okay, the height is given by a parabola. So let's say f of x is equal to x square when x is between minus a and b. That doesn't look good. Just a second. I'm blocking, okay. Now you can read. So the function here has some value, it becomes whatever. Here it has some value, some functional form. But in this region, I'm saying in this region, I'm giving you that it has a shape of a parabola. Exact functional form is f of x is x square. Okay, that is all is what is relevant for me in this exercise. Okay, so now that you guys are expert of it, if f of x is x square and I am interested only in this region, then the first derivative, which gives you the slope, did I define first derivative, second derivative? No, I didn't define. So the derivative gives you the slope, which is 2x. Okay. Now you remember, to know whether you have a maximum or a minimum, local maximum or a minimum, you should find those points. Okay, if you have a local maximum or a minimum, then the derivative is 0 at that point. So if you are interested in finding local maximum or minimum, you should put derivative equal to 0 and find those values of x which give you derivative equal to 0. Okay, so I put f prime of x equal to 0, which means 2x. So f prime of x is what? It is 2x, right? So 2x is equal to 0, which means x is equal to 0. So you see, once you have chosen the functional form to be x square, it's telling you that the slope is 0 at x equal to 0, right? Now, from the graph, from the figure, it's clear that you have a minimum, but that's not what we are after. What we want to say is, given this, can I tell whether I have a minimum or a maximum? And I already know the condition, right? Slope of the slope at the place where slope is 0 should be negative. Remember that? Those we have talked several times. So let's see. So now I know that x equal to 0 is a candidate for local maximum or minimum. Okay, again this statement is not accurate. It's not really completely correct, but we will proceed with this. Okay, f prime being 0 does not necessarily mean that there will be a local maximum or a local minimum. See, what we have argued is, if you have a local maximum, then the slope should be 0. If you have a local maximum, then the slope is 0. But converse might not be true.
Is there an example of the slope being?
Yes, there is, and we will come to that later, okay? Yeah, that kind. But you understand, just because you have seen that if you have a local maximum or a local minimum, slope is 0, doesn't mean that whenever slope is 0, you will have local maximum or minimum. A implying B doesn't necessarily mean that B implies A, okay? So, for now, let's go ahead with this, and I will later tell you what happens. I mean, in which case it will not work out. So, x equal to 0 is a candidate for a local maximum or a minimum, and I should still figure out whether it's a local maximum or minimum from these part, okay, without worrying without looking at the figure. So, let's see whether, so now what should I figure out? What do I need to do?
Slope of the slope.
Slope of the slope, which is, so slope is what? Slope is, very good. Slope is what? D over dx, f of x, right? So, I have d over dx, f of x, that's the slope, right? That is what is called f prime. Now I should, but this is a function, this function is in this case 2x. Now take that function and take its derivative. That's slope of f, and this is slope of slope. And at every point x, what is the value? I take 2x, this is d over dx of 2x, right? I have substituted the slope, and what is that? 2, very good. Now in this case, this is a special example, okay? Because you have a parabola in that region. By the way, I should be careful, f of x is x square when x is between minus a and b, where a and b are positive numbers. So here it is minus, okay? A is greater than 0, b is greater than 0, okay? So this all is true for this region, okay? It's true everywhere.
X less than B.
Very good, thanks. Okay? Now, if this was not really a parabola, but let's say something going like this, then the slope of the slope will not come out to be a constant. In general, it will also be a function of x, right? Imagine if it was x to the 4, then the shape will be roughly this. Okay? It will be parabolic kind of thing, but going even faster upwards. And if you take the slope or the first derivative or the derivative, you will get 4x cube. You again take slope, you will get 4x cube, 4 into 3, 12 x square. So that result depends on x, okay? But in this case, it's a constant. Now, is the 2 is a positive number. And since the slope of slope or slope of slope is positive, this has to be a minimum, right? So, this is point x equal to 0 is a local minimum. See, I will just tell you what the, okay, first let's finish this. Is this okay? Right? So you are asking when, I was saying that does not necessarily mean a local maximum or a minimum. See, for local maximum or minimum, you had this condition that the slope of slope should be either, if it is positive, it gives a local minimum, it's negative, it gives a maximum. But what if slope of slope also comes out to be 0? That can happen, right? No. That would mean if your function is constant. No, that is a constant function. Then every time you take a slope, it's 0 anyway. Okay? So it might happen that the slope is 0, so you think, okay, either a maximum or a minimum. but then slope of slope is also 0. But then to have a local maximum or a minimum, you should have either a negative or a positive, right? The slope of slope. Is that okay? Okay. So, where are we? Now maybe before going further, let's have some terminology. We are saying too much of slope and slope of slope. So if you have a function f of x and you take the slope, meaning d over dx f of x, meaning take the derivative, okay, it is called first derivative or just the derivative. First derivative of f, of the function f. If you take the derivative of this function, okay, also we call it f prime of x, right? When I put 3 of these, it means this is a definition or these are identical statements. So if either you write d over dx f of x or f prime, then you can take this one and also differentiate it. Okay, this procedure of taking a derivative is called differentiation. Okay, I think I didn't say this earlier. Taking derivative of a function is called, this process is called differentiating a function. So if you differentiate the first derivative, okay, then we write f double prime of x. That's the notation, okay? Is it on the camera? F double prime. F double prime, and this thing, instead of writing d over dx and again d over dx, you can also write it as okay, that's a shorthand notation for this, meaning you differentiate the function twice. Okay, so this is called second derivative. Now why do we have this mystery? Second derivative of f. If you take a derivative 3 times, so you take the function f of x and then you differentiate thrice, then it is denoted by, it can also be denoted by 3 primes, and here in this manner. Okay, it's the same. These are, that's the third derivative. Third derivative of f of x, and if you differentiate n times, then this notation is this, and this is called nth derivative. And you might be thinking like, who will differentiate it so many times? Why would you ever do that? Actually, it is done and it's very, very useful. I think you guys are too young to encounter that, but the moment you grow up a little bit more, you will encounter derivatives of all orders. Okay, so they are. It's not just a notation; it's very useful also. Okay, good. Notation is clear, right? So let's go to the next page. I hope you have written down. If not, while you write, it's okay. Okay, yeah, you write it down now. So now I can all our understanding of what is local maximum, local minimum, we can write in this language, and it's important. Okay, it will be also easier to keep it in memory. So what's the condition for local maximum Condition for local maximum, meaning what's the condition that a given point is a local maximum. So first thing is its derivative the derivative at that point should be 0. Okay? Okay, another notation. Before that, I will just, so just a second. So here, if you have a function f and you want to know the value of this function at a point x naught, then you write f of x naught. Okay? That gives you the value of function at point x naught. If you want to know the derivative at that point, we say f prime of x naught. Okay, instead of x, I am just writing x naught, nothing special. So, condition for, let me write it properly. Okay. What happened? Condition for a point x naught to be a local maximum is, first condition is you should check whether the derivative at that point is 0. If the derivative is not 0 at that point, there is no way that the point x naught will be a local maximum or a minimum. So that's condition number 1. What's the condition number 2? F, the second derivative, should be negative. Is that okay? Okay, I am just rewriting everything in this new notation. That's all what I am doing. Condition for a point x naught to be a local minimum is, again, the derivative at that point x naught should be 0, the first derivative, and the second derivative at that point x naught should be, this is minimum, should be 0, more than 0, okay, greater than 0. Is that okay? Fine. Okay, so I'll give you another example now. Okay. So, yeah, okay. I'll give you the graph later. First, let's have this thing. So, suppose you are given a function f of x, which is sine of x, and it is in the region, so I am restricting to to 2 pi. Okay, that's the function. So you know what sine of x looks like, right? So sine of x, okay, fine. So I want to know at what values of x, if at all any, is this function having a local maximum or a local minimum? Does it have any local maximum or local minimum? So what should I do? I should take the first derivative. What is f prime of x in this case? Cos of x. Okay. So what should I do next?
Cos of x equals to.
Very good. Cos of x is equal to 0. Those values of x which satisfy this will be the candidates for local maximum or minimum. Okay, provided the second derivative at that point is not 0. Is not 0. If it is 0, then I told you, right? Then I cannot necessarily say that. Okay. So, but remember, we are going to restrict in this region. We have to find the zeros. So we say we have to find the zeros of cos in this region, okay? So let's look at cos of x. Okay, so let's say this is pi, that's pi by 2, or no, if I take it pi 1, 2, 3, okay, that's not nice. Pi by 2, okay, let's say this is pi by 2. So this is pi over 2, this is pi, this is 3 pi over 2, this is 2 pi, okay, and this is minus pi over 2, and here you have pi over 4. Is that fine? Let's take this to be 1 and let's take this to be minus 1. And I am going to plot cos of x here. Okay? I want to know where these things are 0 from this graph. I guess you already know. So cos 0 is 1, cos pi by 2 is 0, cos pi is minus 1, okay? And cos 3 pi by 2 is 0, cos 2 pi is 1. Okay, and then here at cos minus pi by 2 it's 0. So the function has this it looks like this. No, not this, not this. Okay, here. So let's see. Okay, it's like this. So at what values, and you are restricted to this region, right? From this to this. Is this visible?
Yes.
I will just take that.
I'll zoom in.
Sorry?
I'll zoom in.
No, I will make it big. Shall I make it big? Just a second. That's pi by 4. Pi over 4. What happened? Oh, it's at an angle. Is that okay? So from here to here, cos of x becomes 0 at this point and that point. Right? So what are the solutions of this equation? We have x naught, meaning the place where the derivative is 0. You have, what are the values? Pi over 2 and 3 pi over 2. Right? We have two places. Correct? Now let's look at the second derivative. So these are your candidates. These are the candidates, okay? You can ask me if you have an issue. Now, to know whether this one is a minimum or that one is a minimum or both are minimum, I should ask what's the second derivative and what's the sign of it. I don't need to know the value of it. All I need to know is the sign of it. Is that okay? So let's look at second derivative, f double prime of x. What is that? What's the derivative of cos of x? What's the derivative of cos of x?
Minus sine.
Excellent. Now what I want to know is, so remember, even though I don't need to know more than the sine, but I'm getting entire thing for free, so I'll anyway evaluate. So what is f double prime at pi over 2, and what is f double prime at 3 pi over 2 at our candidate points? If I know those values, I will know the sign of them, and then I can declare it to be either a local maximum or a minimum, okay, whatever it is. So what's f double prime of pi over 2? So what is sine? So this is minus, see that's the f double prime, right? So in this I am substituting x equal to pi over 2. So minus sine pi over 2. What is sine pi over 2? Sine 90 degrees 1. So it's minus 1. What is sine 3 pi over 2? So, so f double prime evaluated at 3 pi by 2. So that is minus sine 3 pi over 2. How much is this? Cannot be 0. How much is sine 3 pi by 2?
Minus.
Hmm?
Oh, sorry, 0.
Cannot be 0. How much is it? This sine 3 pi by 2 is minus 1. That is minus makes a plus 1. You don't understand? Okay, so I'll tell you how. Let's find out sine 3 pi by 2.
I didn't hear.
Array, what is sine 3 pi by 2? Sine 3 pi by 2 is 1. Sorry, minus 1. I'll show you. Here, look at this. If you are not able to recall, I'll just show you. So let's go to the next page. I'll come back here, okay? So what is sine 3 pi by 2? Sine 3 pi by 2 is sine of pi plus pi by 2. Okay, let's look at this. That is, this is pi. So here to here is pi, and this is 3 pi by 2. Okay? So you see this is negative, right? So this is negative.
No, understood.
Okay? It's minus 1.
Minus 1.
This is 1. So you just take a unit circle, right? Take a unit circle, and this angle is 3 pi by 2.
Yes, sir.
So it's minus 1. Okay, so I hope this is clear. So minus 1 times minus 1 is plus 1. So at x equal to pi by 2, where the first derivative is 0, the second derivative is negative, which means x not equal to pi by 2, pi over 2 is a local maximum, right? And the other one is a local minimum. Is that okay? So pi over 2 is maximum, 3 pi over 2 is minimum. Let's see. Let's plot sine of x and just confirm whether what we have gotten by derivation is correct. See, here you might be wondering, why are you doing this at all? I know everything about sine of x. You could have just seen this. I'm just giving you practice. If I give you another function, let's say I give you sine x plus cos x, then what are you going to do? Or I give you some other function, x times sine x plus x square cos cube x plus whatever. Then you just follow this procedure and you figure it out. Okay? So local maximum, local minimum. I will plot on this graph itself sine of x, and then we'll confirm that this is correct. I guess you already know that.
Can you plot on another graph? The graphs are very small.
Sorry?
That graph is very small.
Small. Okay, so
Plot on a new graph.
you want, then I'll have to draw this entire thing again.
Huh,
Is
there is-
there a way to
Huh,
make it
yeah,
big?
just make it bigger,
Oh, there is a way. Nice. Oh, that's cool.
That's better.
Looks horrible, but it's cool. So, I take this. Okay, so I want to plot here sine of x, because that was my function, right? Sine of x, in your notes you can see. So sine 0 is 0, sine pi over 2 is 1, sine pi is 0, sine 3 pi over is minus 1, here, somewhere here, 2 pi is 0, okay? And on that side, at minus, here it will be minus 1. So the function is like this. Looks horrible. It's fine. Okay, it should be like this. Again, even worse. Okay, let's try like this.
Yes, that's nice.
Got it? Good. So let's see. We see that our function, which was sine of x, our calculation is telling that at x equal to pi over 2, you should have a local maximum. At x equal to pi over 2, you of course you have a local maximum. At x equal to 3 pi over 2, you should have a local minimum. At x equal to 3 pi over 2, you have a local minimum. Okay, so our algebra is perfect. Okay, agreed? Now you might have wondered, why do all this? Why should you do all that? And if you are wondering why you should do all that, I'll give you a homework. And then you will know why you should do all that. Oh, this is ugly.
Slide. No, that.
Even better, go to the next page. Okay, so take this function f of x, homework. Okay, homework. Take function to be sin x plus cos x. Okay, find all the local maximum and minimum and minimum points, all the points at which there is a local maximum or a local minimum, local maximum or a local minimum. Okay, can you do that? You understand this? First step is take f prime of x, put it 0, find the solutions of that equation, then take second derivative, check at those points at which you have found f prime of x to be 0, what's the value of sin f double prime of x, the second derivative. If it is positive, it's a local minimum. If it's negative, it's a local maximum. Right? If you insist on another homework, I think you insist, so I'll give you. Very good. So take sine of x plus sine of 2x. Okay, it will also give you practice with taking derivatives. One more? Okay, take one more. X sine x plus cos square x. Okay, by cos square of x, I mean cos of x whole square. Take that also. and if you are interested, make some problems for yourself. And it's a good idea to make something for yourself. Now this is useful, this analysis is useful. See, if you want to, okay, write it down. Suppose you are given some function, okay? You want to know what it looks like roughly, where it is minimum, whether there are hills and valleys in that, okay? How will you do it? By this analysis. If you don't do that analysis, you wouldn't know, okay? So that's why it's very useful to do this. And less importantly, it also comes in exams, okay? So, okay. Now I'll show you something cool and extremely important. So important that no matter how much you grow up, if you remain in academics, even otherwise also, that equation keeps coming over and over again in your life. Okay? So I'm going to show you that equation. So take function f to be sine of x. Take its first derivative. What is the first derivative of sine? What is the derivative of sine of x? That's cos of x. Take its derivative again. Okay, that's the second derivative, right? I'm differentiating it twice, which means I should take the derivative of this function. What's the derivative of this function? It's the derivative of that thing. Minus sine of x. You see, you started with f of x to be sine of x, you took its derivative, it gave you cos, taking derivative again gives you sine with a minus sign, which means d2 over the square of f of x, where f of x is sine of x, is equal to minus d over dx f of x. Sorry.
It's f of x.
Okay, where f of x is sine x. Okay, or I will just write it as, yeah, that's it. If you want, you can bring it to zero, left side. So I will just also write it as d2 over dx squared. Nothing spectacular is happening in this one. It's the same content. If f of x is equal to, okay, can you think of any other function for which this will be satisfied? So this statement that if you take the second derivative, it will equal the minus of its value. Okay, if you take the second derivative of function, it's equal to the negative of that function itself. That is true if f is sine of x. That's what I have shown to you. Can you think of any other function for which this will be true?
Cos.
Very good. Because if you take, let's say, f of x to be cos of x, first derivative will be minus sine of x, and the second derivative is differentiating this will give you sine, will give you cos of x, and that's minus, which is this. So f double prime is equal to minus f for cos. Can you think of any other function? No? Tan.
No, that will be better.
Tan. Okay, so exercise. Find
I don't think.
the second derivative of tan function. Okay, find out what it is, and you will see that that is not going to happen.
That's not.
Can you think of any other function for which this will be true?
Sine of x plus cos of x.
Excellent. Correct. Why?
Because when you take the derivative of two functions
Sum of two functions.
sum of two functions, it's equal to the derivative of one function plus the derivative of the other.
Very good.
And that is equal to minus the first function plus minus the second function.
Very good. Because of that property that the derivative of sum is sum of derivatives, that's going to work out. Excellent. Sine of x plus cos of x will also satisfy. Very good. So, if you take f of x to be sine of x plus cos of x, then the second derivative will be equal to minus f of x. Very good. Any other? Can you think of any other function which will satisfy this equation? Very good. Excellent.
It's a constant.
Which is constant? What is constant?
And f of x is a constant.
No.
Sorry.
F of x is constant. The first derivative is 0. The second derivative is 0.
Oh, no, sorry. When,
No. So, I'll tell you. Whatever you said, that argument will apply for this also, right? Imagine some constant a, whatever that is, times sine of x plus some constant b times cos of x.
that's
That will also go through. Okay? Is it clear? So let's see. F prime of x, the first derivative is what? A cos of x minus b, because the derivative is minus sine of x, that is the minus sign here, minus sine of x. Taking the second derivative gives you minus a sine of x, okay, because the derivative of cos is minus. And as you can see, this is just the negative of that, right? So it is minus f of x. Is that okay?
yes.
Even though we are not doing what I am about to say, but now since we have done it, let me tell you. This equation is called simple harmonic equation. Okay? And from our experience, we were just playing with derivatives, right? We were just playing with derivatives. We came up with some observation and we said, okay, we found what we find is, oh, if you have this equation, then these are the solutions, and there is a name given to this. I will tell you later why this equation is important, and you will see that it comes at many places. Okay, I'll give you physical examples later. So I think I'm done with all that I wanted to say for this lecture. So yeah, please do the homework. That will be fun. And learn to create problems for yourself. I mean, not problems in life, but such problems for yourself. Okay. Create simple problems. It's extremely important thing to do. Okay, so we'll stop here unless you have some question to ask. You have studied simple harmonic motion, right? In school? No. It never happened in your life? Okay. So anyway, that's simple harmonic question. So I will stop here. Okay, good.